Humanity is trapped on a single planet, and that is a dangerous situation. By the end of this video, you will understand the 25 milestones that turn our fragile presence on Earth into a self-sustaining civilization across worlds. Some of these steps are already being tested, while others lie centuries ahead. What will it take to break our dependence on one world and build a future among the stars? The journey begins with the very first step, rethinking how we leave our home planet. Which milestone do you think will be the hardest to achieve? The first milestone is the one that changes the economics of spaceflight itself. For decades, every rocket was a one-time use machine. After delivering its payload, the entire vehicle would fall into the ocean or burn up in the atmosphere. That meant each launch cost hundreds of millions of dollars, and the price tag alone made most grand ambitions impossible. You cannot build a city on Mars if every trip costs as much as a small country's yearly budget. Reusable rocket technology flips that equation completely. Think of it this way. If commercial airlines threw away their planes after a single flight, air travel would be a luxury reserved for the wealthiest people on Earth. Only the richest nations could afford to move goods or people across oceans, but because planes are reused thousands of times, the cost per trip drops to a fraction of the original price. Rockets are finally following the same logic. SpaceX proved this was possible with the Falcon 9. Instead of discarding the first stage, they equipped it with landing legs and grid fins. After separation, the booster fires its engines again, steers itself through the atmosphere, and touches down on a drone ship or a concrete pad. At first, skeptics called it a stunt. But after dozens of successful landings, the pattern became clear. Reusing that booster cuts launch costs by roughly 80%. What once cost $60 million can now be done for a fraction of that amount, as long as the rocket flies again and again. Starship pushes this idea further. It is designed to be fully reusable, both the booster and the upper stage. Instead of a tiny capsule on top, Starship is a massive stainless steel vehicle intended to carry cargo, fuel, and people. Blue Origin's new Shepard demonstrates reusability on a smaller scale for suborbital tourism, but the principle is the same. Land the vehicle, inspect it, refuel it, and send it back up. This shift from expendable to reusable is the foundation for every other milestone on this list. Without cheap and frequent access to space, building a space station, mining an asteroid, or establishing a colony on Mars remains a fantasy. Reusability turns the impossible into a question of engineering and scale. So once we master landing boosters reliably, the next challenge becomes obvious. How do we launch them often enough to make a multi-planetary future real? A fully reusable rocket solves half the problem. The other half is fuel. Every kilogram of propellant you carry from the ground is mass that must be lifted through Earth's gravity. That means the bigger your destination, the more fuel you need, and the heavier your rocket becomes. Eventually, you hit a wall where no single launch can carry enough propellant to send a mission to Mars. Orbital refueling is the way around that wall. Instead of launching a fully fueled spacecraft from the ground, you launch it empty or with just enough propellant to reach orbit. Then you send up separate tanker flights to deliver the fuel in orbit. The spacecraft docks with a depot or directly with a tanker, transfers the cryogenic propellant, and tops off its tanks before heading deeper into space. This changes everything. Think of it like a road trip. You do not load your car with enough gasoline for the entire journey before leaving your driveway. Instead, you drive to a gas station along the highway and fill up there. The gas station is already stocked by multiple deliveries. In space, the orbital depot is that gas station. The tanker flights are the delivery trucks, and the spacecraft leaving for the Moon or Mars is the car that refuels just before the long stretch. The technical challenge is enormous. Cryogenic propellants like liquid hydrogen and liquid oxygen are extremely cold, around -420 degrees Fahrenheit for hydrogen. In the vacuum of space, keeping them from boiling away is difficult. Without gravity, the liquid does not settle at the bottom of a tank the way it does on Earth. It floats around in blobs, transferring that floating liquid from one tank to another without losing it to vapor requires careful engineering. You need special nozzles, pressure management, and maybe even a slight rotation to create artificial gravity inside the tank. SpaceX is tackling this with their Starship program. They plan to test orbital refueling by docking 2 Starships in low Earth orbit. One will act as a tanker and transfer propellant to the other. If successful, it will allow Starship to carry a fully fueled upper stage to the Moon or Mars without being limited by what it could lift from the ground. NASA has also invested in studies for orbital depots and cryogenic fluid management. The advantage is clear. With orbital refueling, a single rocket design can serve multiple roles. You launch the same vehicle as a cruise ship, a cargo hauler, or a tanker. That lowers manufacturing costs and simplifies logistics. Once you have a depot in orbit, you no longer think of launches as individual missions. You think of them as supply runs that stockpile fuel for an expedition. The first practical use of this capability will be for lunar missions. Instead of carrying all the fuel needed to land on the Moon and return, a spacecraft can refuel in Earth orbit, then head to the Moon with a full tank. That extra fuel means you can carry more cargo, more scientific equipment, or more supplies for a surface base. In fact, a permanent lunar outpost depends on orbital refueling. Without it, every trip to the Moon would require a dedicated heavy launch, and the cost would remain too high for regular supply runs. With it, you can send tankers ahead of time to store fuel in a depot near the Moon, creating a supply chain that supports continuous habitation. The same logic applies to Mars. A crewed Mars mission needs thousands of tons of propellant to slow down upon arrival, land, and eventually launch back home. That fuel cannot all come from Earth. Orbital refueling allows you to assemble the mission in pieces, refuel in Earth orbit, and later refuel again at a Martian depot using local resources. This milestone is the bridge between a single launch and a true interplanetary transportation network. Once we master moving fuel in orbit, the Moon becomes a regular destination instead of a historic exception. And that sets the stage for building something permanent there. A permanent outpost on the Moon will be humanity's first true home beyond Earth. Unlike the Apollo missions where astronauts stayed for a few days, this base is designed for continuous habitation. Crews will rotate in and out, living and working on the lunar surface for months at a time. The experience gained there will determine whether we can ever survive on Mars. Building the base requires habitat modules that shield occupants from the harsh environment. Early structures might be inflatable or assembled from prefabricated pieces delivered from Earth. But the real game changer is using the Moon's own resources. The lunar poles contain water ice in permanently shadowed craters. Miners can extract that ice, melt it, and split it into oxygen and hydrogen through electrolysis. Oxygen supports breathing and can be used as oxidizer for rocket engines. Hydrogen becomes a clean fuel. This capability, called in-situ resource utilization, reduces the need to haul supplies from Earth. A single ton of water ice could produce enough oxygen for a crew of 4 to breathe for over a year. It also yields propellant for return trips or for refueling landers bound for deeper space. Power comes from the Sun. The lunar day lasts about 14 Earth days, followed by 14 days of darkness. Solar arrays can provide energy during the day, but batteries or other storage technologies are needed for the long night. Another option is placing solar farms on crater rims that catch nearly continuous sunlight near the poles. NASA's Artemis program intends to land the first woman and the next man near the South Pole, precisely because of those ice deposits and the favorable lighting conditions. The Lunar Gateway, a small orbiting outpost, will serve as a staging point. Astronauts will transfer from the gateway to a lander and descend to the surface. The gateway also supports scientific experiments and communications relay. International and commercial partners are already contributing. The European Space Agency is developing modules for the gateway. Japan and Canada are involved in robotics and life support. Private companies like Blue Origin and SpaceX are building landers and cargo delivery systems. This collaboration spreads the cost and brings diverse expertise. It also demonstrates that off-world living does not have to be a single nation's project. It can be a shared human endeavor. Radiation protection is a serious challenge. The moon lacks a magnetic field and thick atmosphere. Solar flares and cosmic rays pound the surface. Habitats will likely be buried under a layer of lunar regolith, the powdery rock that covers the ground. That soil acts as a natural shield. Rovers and spacesuits will carry shielding as well. Early bases might use sandbags filled with regolith placed on top of inflatable domes. Over time, 3D printing robots could build walls from compacted lunar dirt. The moon is the perfect testbed for Mars. Its gravity is 1/6 of Earth's compared to Mars 1/3. That means systems designed for reduced gravity can be proven here first. Life support, recycling, food production, psychological resilience, all of these can be validated 250,000 miles away from home. If something breaks, a rescue mission from Earth takes 3 days instead of 9 months. That margin of safety allows engineers to push the limits and learn from failures without risking a crew stranded on Mars. Each successfully completed rotation on the moon teaches us how to manage resources, handle emergencies, and maintain equipment far from Earth. The base becomes a training ground for the next generation of explorers, and once the technology matures, the steps that kept humans alive on the moon will be adapted for the long journey to the red planet. The lunar base is not the final destination. It is the school that teaches us how to reach for the next world. The moon and Mars are not barren wastelands. They are treasure chests of raw materials waiting to be unlocked. In-Situ resource utilization, or ISRU for short, is the practice of using what is already at your destination rather than hauling everything from Earth. This single concept slashes the cost of a colony by orders of magnitude and makes permanent settlement economically viable. On the moon, the most valuable resource is water ice trapped inside permanently shadowed craters at the poles. A robotic miner could drill into that ice, heat it, and collect the vapor. A single ton of water yields roughly 111 kilograms of hydrogen and 889 kilograms of oxygen through a simple process called electrolysis. An electric current splits the water molecules into their component gases. The oxygen becomes breathable air for habitats and oxidizer for rocket engines. The hydrogen becomes clean fuel. Using that hydrogen with more oxygen in a fuel cell generates electricity and pure water as a byproduct, closing the loop. That means a small mining operation could provide all the resources needed for a lunar base without a single resupply tank from Earth. Mars offers even more potential. The Martian atmosphere is 95% carbon dioxide. In the early 1900s, a French chemist named Paul Sabatier discovered that carbon dioxide and hydrogen can react over a catalyst to produce methane and water. That reaction, now called the Sabatier reaction, is the key to making rocket fuel on Mars. Here is how it works. Bring a small amount of hydrogen from Earth, combine it with carbon dioxide drawn from the atmosphere, and out comes methane, the same fuel used in many rocket engines, plus water. The water can be electrolyzed again to produce more oxygen and hydrogen, and that hydrogen is fed back into the Sabatier reactor. The only inputs are a little hydrogen seed and electricity. The output is vast quantities of propellant. To put it in perspective, a single Starship-sized vehicle needs roughly 480 tons of methane and oxygen to launch from Mars back to Earth. Hauling that from Earth would require dozens of additional launches, but a small factory on Mars, powered by solar panels or a nuclear reactor, could produce that propellant using local resources. NASA tested this concept in a small way with an instrument called MOXIE on the Perseverance rover. MOXIE stands for Mars Oxygen In-Situ Resource Utilization Experiment. It works like a reverse fuel cell. It pulls in Martian air, compresses it, and splits the carbon dioxide into carbon monoxide and oxygen. The carbon monoxide is vented and the oxygen is stored. Over several runs, MOXIE proved it could produce about 10 grams of oxygen per hour. That is a laboratory-scale demonstration. The next step is a full-scale ISRU plant that can produce a ton of oxygen per day. Such a plant would not only provide rocket propellant but also breathable air and water for a Mars base. The same equipment can be adapted for the Moon. Instead of pulling carbon dioxide from the atmosphere, lunar ISRU plants will process regolith, the dusty surface material, to extract metals, silicon, and oxygen. A technique called molten regolith electrolysis heats the soil until it melts, then passes an electric current to separate oxygen from the metallic elements. The oxygen bubbles out and can be collected, leaving behind a solidified metal alloy that can be shaped into construction materials. This turns dirt into survival supplies. Building habitats, roads, landing pads, and spare parts from local materials means only specialized equipment and electronics need to be shipped from Earth. The weight savings are enormous. The goal is not just to reduce resupply costs but to make a colony self-sufficient. Once ISRU works reliably, humans are no longer explorers who visit and leave. They become settlers who can stay. With that foundation laid, the next urgent challenge emerges. How do we keep those settlers healthy when they are months away from the nearest hospital? Every crew leaving Earth carries a ticking clock. No matter how much food, water, and oxygen you pack in the cargo hold, those supplies dwindle with each passing day. On a multi-year mission to Mars, a stockpile big enough for the whole journey would weigh far too much to launch in a single rocket. The only solution is to stop treating air and water as consumables and start recycling them almost completely. That is exactly what closed-loop life support systems are designed to do. They take the waste products from a crew, carbon dioxide, urine, sweat, moisture from breath, and convert them back into clean water and breathable air again and again. The International Space Station already does this, but only partially. A system called the Water Recovery System distills urine and collects humidity from the air, then filters and treats that water until it is purer than most tap water on Earth. That hardware recovers about 85% of the water used by the crew. The remaining 15% is lost in the form of brine or during cleaning cycles. Oxygen is generated by a device called the Oxygen Generation Assembly, which uses electricity to split water molecules into hydrogen and oxygen. The oxygen is supplied to the cabin, while the hydrogen is either vented or combined with carbon dioxide in a Sabatier reactor to produce methane and water. That water can then be fed back into the system. But even with all that, the station still relies on regular resupply shipments from Earth to top off water tanks and replace failed parts. For a spacecraft heading to Mars, that resupply is impossible. The crew must achieve near 100% closure, meaning almost every molecule of water and oxygen must be recovered. Several advanced technologies are in development to push recycling rates higher. One promising approach is the algal bioreactor. Certain strains of algae, such as spirulina, grow rapidly in a nutrient-rich solution. They consume carbon dioxide and produce oxygen through photosynthesis. In return, they need light and a steady supply of minerals. The algae can be harvested as a food source or processed into a nutritional supplement. A single reactor the size of a small suitcase could provide enough oxygen for one person, while also purifying wastewater through a process called phytoremediation. The trade-off is that algae require careful temperature and pH control, and they can become contaminated, but they offer a renewable, biological backup to mechanical systems. Mechanical carbon dioxide scrubbers are already standard on spacecraft. On the ISS, a device called the Carbon Dioxide Removal Assembly uses a material called zeolite to absorb CO2 from the cabin air. When the zeolite is heated, it releases the captured gas, which is then vented overboard. On Mars, that CO2 could instead be fed into ISRU equipment to make propellant. Future scrubbers might use a newer technology called solid amine sorbents that are more efficient and require less energy to regenerate. Hydroponics and aeroponics allow astronauts to grow fresh vegetables in a controlled environment. Plants absorb carbon dioxide and release oxygen, but they also purify water through transpiration. The moisture released from leaves is collected and recycled into drinking water. A greenhouse module on a Mars transit vehicle could supplement the crew's diet with leafy greens, tomatoes, and herbs. Beyond nutrition, caring for plants has a psychological benefit, a splash of green in a sterile metal tube. However, growing enough calories to feed a crew of 4 for a year would require a room the size of a small house. So for the bulk of their energy, astronauts will still rely on packaged food from Earth. But every plant adds a tiny amount of closure to the life support loop. Waste-to-food conversion is still experimental but holds huge potential. The idea is to take leftover food scraps, paper, and even human waste and process them into an edible substance. One method uses a reactor that applies heat and pressure to break down organic material into a slurry. Then microbes or enzymes convert that slurry into a nutritious protein-rich paste. Another approach uses engineered bacteria that feed on urea, the main nitrogen compound in urine, and produce amino acids or fatty acids. While the idea might sound unappetizing, the crew would likely consume the product after further processing or use it to fertilize plant beds. On a multi-year mission, every gram of mass matters, and turning waste into food closes the loop even further. The challenge is achieving stability and reliability over thousands of days. A single pump failure or a bacterial contamination could cripple the system. Engineers must design redundant backup units and procedures that allow the crew to repair or replace critical components with tools and spare parts they carry. Testing these systems in a simulated Mars environment on Earth, such as NAS, a Habitat for Human Exploration research analog, helps refine the technology. But the true test will come during a long-duration mission far from home, where no resupply capsule can reach them. In the end, closed-loop life support is the invisible backbone of any interplanetary journey. Without it, the crew would run out of air or water long before they saw the rust-colored plains of Mars. And after their breath is recycled, the next essential need is what goes into their stomachs: fresh, reliable food grown in the void of space. Fresh vegetables in space are no longer a luxury. They are a necessity for any crew that plans to spend years away from Earth. The first bite of a space-grown tomato marks a turning point in human independence from our home planet. For decades, astronauts relied on prepackaged meals that were nutritious but bland. Freeze-dried ice cream and rehydrated pasta work fine for a week-long shuttle mission, but on a 3-year round trip to Mars, monotony becomes a real problem. Lack of variety in texture and flavor can lead to menu fatigue, where crew members eat less and lose weight. Worse, the carefully balanced vitamins and nutrients in packaged food degrade over time. A 5-year-old vitamin C packet loses most of its potency. Growing fresh food on site solves both of those issues at once. Hydroponics is the simplest method for space. Plants grow with their roots suspended in a nutrient-rich water solution. No soil is needed. The water circulates through a closed system, so nothing is wasted. Aeroponics takes it a step further. The roots hang in a mist chamber where fine droplets of nutrient solution are sprayed directly onto them. This uses less water and exposes the roots to more oxygen, which can accelerate growth. Both techniques work well in microgravity as long as you control the water carefully. On the International Space Station, astronauts have been testing these approaches for years. The veggie experiment is a small plant growth chamber about the size of a carry-on suitcase. Inside, a fabric pad holds seeds in place while LEDs provide a specific spectrum of light. Red and blue wavelengths are most efficient for photosynthesis, but a few green LEDs are added so the plants look natural to the human eye. The first crop was red romaine lettuce. It grew for about 30 days before harvest. Since then, the crew has successfully grown zinnias for a splash of color and even a small crop of radishes. The advanced plant habitat is a larger, more automated system. It has sensors that monitor moisture, temperature, and carbon dioxide levels. A control system on Earth can adjust conditions remotely. In this habitat, researchers grew dwarf wheat and a type of mustard greens called Tokyo Bicana. The results showed that plants can complete a full life cycle in space from seed to seed. That is critical because it means future crews could save seeds from one generation to plant the next, creating a self-renewing food supply. The nutritional benefits are clear. Fresh produce provides vitamins that degrade in stored food. Leafy greens and peppers are rich in vitamin C and folate. Tomatoes contain lycopene, an antioxidant that may help protect cells from radiation damage. Potatoes are a dense source of carbohydrates and potassium. A single potato plant can yield several pounds of edible tubers, making it a staple for any Mars colony. But the psychological impact is just as important. Astronauts on the ISS report that tending to plants gives them a sense of purpose and a connection to Earth. The simple act of watering a seedling and watching it grow breaks the monotony of a metal and plastic environment. The color green is rare in space, and its presence has a calming effect. On a long voyage to Mars, where the view out the window will be nothing but blackness for months, a small greenhouse becomes a sanctuary. Scaling up from a few lettuce plants to full-scale agriculture is a huge engineering challenge. A single person needs about 2,000 calories per day. To provide a significant fraction of that, a greenhouse on Mars would need to be roughly the size of a tennis court. Light is the biggest constraint. On Mars, sunlight is only about half as intense as on Earth, and the dusty atmosphere scatters it further. That means most greenhouses will rely on artificial LEDs powered by solar panels or a nuclear reactor. The energy cost is high, but it is still far less than the cost of shipping prepackaged food from Earth. The water required comes from ISRU systems that extract ice from the Martian soil or recycle wastewater. Nutrients can be recycled too by composting inedible plant parts like stems and roots. In closed-loop systems, nothing is wasted. The crew will eat the harvest, their waste is broken down, the nutrients return to the plant beds, and the cycle continues. Several research facilities on Earth are mimicking Mars conditions to test this. At the University of Arizona, a project called Prototype Lunar and Martian greenhouses uses inflatable, transparent tubes that could be buried under regolith for radiation protection. Inside, robots tend the crops while sensors monitor every variable. The goal is to make the system fully autonomous so the crew does not have to spend hours each day on gardening. Automated harvesters could pick ripe produce and replant seeds without human intervention. Potatoes are a particularly promising crop for Mars. NASA and the International Potato Center conducted experiments using soil from the Atacama Desert in Chile, which is very dry and similar to Martian regolith. The potatoes grew, though the yields were lower than in Earth soil. With added nutrients and better water management, yields improved. This suggests that with proper engineering, Mars colonists could grow their own starch source, a foundation for breads, soups, and stews. Once the basics are mastered, the greenhouse can expand to include herbs like basil, mint, and chives, which add flavor to otherwise bland meals. Strawberries provide a sweet treat. Even soybeans could be grown to produce tofu or oil. Each crop adds variety, reduces reliance on prepackaged foods, and improves morale. But even the best greenhouse cannot feed a colony entirely. Processed staples like grains and legumes will still need to come from Earth in the early years. Over time, as the colony grows and more greenhouses are built, local production will cover a larger share of the menu. This milestone is not just about food. It is about mental health, nutritional science, and the principle of self-sufficiency. Mastering space agriculture means humans can stay longer, travel farther, and eventually live independently of Earth. And as fresh food begins to flourish in Martian soil, the next invisible threat becomes impossible to ignore. Cosmic radiation and solar storms will bombard those greenhouses and the people inside them, forcing us to find shelter protectively close to the next milestone. Radiation is the silent enemy of every deep space mission. Unlike the vacuum or the cold, radiation cannot be seen or felt until it causes harm. Outside the protective bubble of Earth's magnetic field and atmosphere, space travelers face a constant bombardment of high-energy particles. These particles come from two main sources. The first is the Sun, which occasionally releases powerful storms of charged particles known as solar particle events. The second is galactic cosmic rays, which are fast-moving nuclei from exploded stars that travel across the galaxy at nearly the speed of light. Both pose serious health challenges to any crew on a long journey. On Earth, we are shielded by the planet's magnetic field and a thick blanket of air. A person receives roughly 3 millisieverts of radiation per year from natural background sources. On the International Space Station, which is still within low Earth orbit and partially protected, astronauts receive about 150 millisieverts over a 6-month stay. That is 50 times more than on the ground, but once you leave Earth orbit entirely, the numbers jump higher. A round trip to Mars could expose astronauts to a total of 600 to 1,000 millisieverts, depending on the duration and solar activity. That level of exposure increases the long-term risk of health issues, including certain cancers and damage to the central nervous system. For any multi-planetary species to survive, effective shielding is not optional. It is a non-negotiable requirement. Passive shielding is the most straightforward approach. Simply place a thick barrier between the crew and the radiation source. The barrier absorbs or slows down the particles so they lose their energy before reaching the human body. On a spacecraft, that barrier could be made of water, a material that is excellent at blocking radiation because it has a high density of hydrogen atoms. In fact, water is used in many nuclear reactors on Earth as a shield. A spacecraft could store its drinking water in a layer around the crew quarters. The same water that keeps the crew alive also protects them. Another passive material is polyethylene, a common plastic. It is rich in hydrogen and very effective at stopping cosmic rays. Thin sheets of polyethylene can be built into walls and storage containers. On the Moon or Mars, the best passive shield is the ground itself. A layer of regolith, the dusty surface material, piled on top of a habitat can absorb most of the radiation. Calculations show that a covering of about 3 meters of Martian soil would reduce the radiation dose to background levels similar to those on Earth. That is why future bases will likely be buried or covered with berms. Rovers can use a similar trick by parking in natural caves or lava tubes, but passive shielding has a major downside. It is heavy, water and regolith are dense. Carrying tons of water or plastic from Earth is expensive. On the surface, you can use local materials, but that requires digging equipment and time. During the voyage to Mars, the spacecraft must carry its own shield. That weight competes with cargo and fuel. Active shielding is a different approach. Instead of stopping particles with mass, active shielding uses electric or magnetic fields to deflect them away. This is similar to how Earth's magnetic field works. A spacecraft could generate a magnetic field around itself, creating a miniature magnetosphere. The idea is to create a force that pushes charged particles aside before they reach the hull. Several research groups have explored this concept. The simplest active shield is an electrostatic field. By charging the outer skin of the spacecraft to a high voltage, you can repel positively charged particles like protons. However, electrons from the solar wind are negatively charged and would be attracted, so the system must handle both polarities. More advanced designs use a magnetic loop that extends tens of meters away from the craft. A current running through a superconducting wire creates a strong magnetic field. Charged particles spiral along the field lines and are swept away. This method works well in theory, but requires a lot of energy and careful engineering. The superconductor must be kept extremely cold, and the structure must be robust enough to deploy in space. Plasma shielding is another active concept. A small plasma cloud, an ionized gas, is generated around the spacecraft. Magnetic fields hold it in place. The plasma interacts with incoming particles, absorbing some of their energy and deflecting them. This is still in early experimental stages, but could be lightweight and efficient. The biggest advantage of active shielding is weight. Instead of hauling tons of material, you carry a power source and a magnetic coil. The trade-off is complexity. A failure in the active system could leave the crew exposed. For that reason, most mission plans combine both strategies. A relatively thin passive shield reduces the baseline dose, and an active system handles the peaks during solar storms. On the lunar surface, researchers have measured the radiation environment to better understand how to design safe habitats. The Lunar Reconnaissance Orbiter carried a radiation detector that mapped the dose across the Moon. The results showed that unprotected astronauts on the surface receive about 550 millisieverts per year. With a meter of regolith shielding, that drops to about 50 millisieverts, which is a manageable level for long stays. On Mars, the Curiosity rover has been monitoring radiation since 2012. It found that the surface dose averages about 230 millisieverts per year, roughly half that on the Moon, because Mars has a thin atmosphere that provides some protection. Still, without shielding, a 3-year mission could exceed safe limits. The milestone is clear: develop reliable, affordable radiation shielding that works both in space and on the surface. The technology exists in prototypes, but it must be scaled, tested, and proven over long durations. Once that barrier is in place, the human body can tolerate the journey to Mars and beyond. The next challenge then becomes getting there faster, because a shorter trip means less radiation exposure. That shift leads directly to the propulsion systems that will cut travel time from months to weeks. Chemical rockets are powerful, but they are slow and wasteful for deep space journeys. The next milestone replaces explosive chemistry with the controlled release of nuclear energy to cut travel times dramatically. Imagine a rocket engine that does not burn fuel in an open flame. Instead, it passes a propellant like hydrogen through a nuclear reactor, where atomic fission heats the gas to extreme temperatures. That superheated gas expands out of a nozzle, producing thrust. This is a nuclear thermal rocket. The core difference from chemical engines is efficiency. Chemical rockets convert about 30% of their fuel's energy into thrust. A nuclear thermal rocket can convert over 60%, giving it more than double the specific impulse, the measure of how efficiently a rocket uses propellant. For a mission to Mars, that means you need far less fuel mass to get there. or you can carry much more cargo in the same vehicle. There is also nuclear electric propulsion. Instead of directly heating propellant, a nuclear reactor generates electricity. That electricity powers an ion thruster, which accelerates charged particles, usually xenon gas, to incredible speeds. Ion thrusters are even more efficient than nuclear thermal, but they produce very low thrust. Think of the difference between a race car engine and a sailboat. The race car accelerates quickly but runs out of fuel soon. The sailboat pushes gently but continuously for months. Nuclear electric propulsion works like that sailboat, slow to accelerate, but it can keep pushing for years. Over a long journey, that constant gentle thrust builds up tremendous speed. A spacecraft using nuclear electric propulsion could reach Mars in as little as 3 months, compared to 9 months with chemical rockets. NASA has been studying both approaches for decades. The agency recently announced plans to develop a nuclear thermal rocket for crewed Mars missions. A test flight could happen by the late 2020s. The goal is a demonstration that proves the reactor can operate safely in space and produce enough thrust to move a large spacecraft. Several private companies are also designing compact fission reactors for space. The key challenge is safety. A nuclear reactor must be launched from Earth without risk of contamination. The reactor core is not activated until it reaches orbit, so there is no radiation hazard during launch. Once in space, the reactor is shielded to protect the crew. The spent fuel remains safely contained, and the spacecraft's orbit is chosen so that it never falls back to Earth. Faster transits solve 2 critical problems. Less time in space means less exposure to cosmic radiation and solar storms. The crew's dose is cut by half or more. Shorter trips also reduce the psychological strain of isolation and confinement. Being stuck in a metal can for 9 months is hard enough. 3 months is much more manageable. With nuclear propulsion, the window for a round trip opens wider, making it possible to stay on Mars for a longer surface stay and still return home within a reasonable time frame. Beyond Mars, nuclear propulsion makes the outer planets reachable. Jupiter, Saturn, and their moons are vast destinations for science and resource extraction. A chemical rocket would take years to get there. A nuclear-powered spacecraft can do it in months, opening up the entire solar system to human exploration. This milestone transforms our reach from a single planet to a true interplanetary civilization. The journey from Earth to Mars becomes a commute, not an expedition. And once we can travel that fast, the next step is learning how to land heavy payloads on a planet with a thin atmosphere. The thin atmosphere of Mars makes landing heavy payloads one of the hardest tasks in all of spaceflight. Earth's thick blanket of air slows a capsule down with friction and parachutes. Mars has less than 1% of Earth's atmospheric pressure, so parachutes alone cannot stop a large spacecraft before it smashes into the ground. That is why the first human landing will require a combination of techniques never tried together before. The crew will arrive in a spacecraft that has been traveling for months, likely a Starship or a similar vehicle. Before entering the Martian atmosphere, the ship will separate from its transfer stage and orient itself for entry. The heat shield will face forward, absorbing temperatures that can exceed 1,600 degrees Celsius. That heat shield must be larger and more durable than any used before because the vehicle itself is enormous compared to the small robotic landers we have sent so far. After the initial deceleration, a supersonic parachute deploys. This is not the kind of parachute a skydiver uses. It is a massive canopy, over 30 meters in diameter, designed to open while the craft is still traveling faster than the speed of sound. The timing is critical. Open it too early and the fabric tears apart. Open it too late and there is not enough time to slow down. Once the parachute reduces speed to around 400 kilometers per hour, retropropulsion takes over. Retropropulsion means firing engines downward to create a cushion of thrust that slows the vehicle to a gentle hover. The same engines that powered the spacecraft through space now fire in short pulses, adjusting to the changing altitude and velocity. Sensors on the underside scan the surface for hazards like boulders or steep slopes. The flight computer selects a safe landing site in real time, then guides the vehicle to a soft touchdown. For a mission using the sky crane technique, the descent stage would hover above the ground and lower the crew capsule on cables. That method worked flawlessly for the Curiosity and Perseverance rovers, but scaling it up for a human-rated vehicle adds enormous complexity. The more likely approach for early crewed missions is direct retropropulsive landing, where the entire spacecraft sets down on its own landing legs. SpaceX plans to use this method with Starship. The vehicle has 6 powerful engines at the base. During landing, only a few of them fire, throttling down precisely to control the descent. The legs deploy outward just before touchdown, absorbing the final impact. NASA is also studying a hybrid approach called the Mars Lander concept, which separates the crew capsule from the cargo section before landing and uses different braking systems for each. The moment of touchdown will be silent. No cheering from mission control can reach the crew at that distance, because radio signals take several minutes to travel from Mars to Earth. The astronauts will be the first to know they have arrived. After months of living in a cramped spacecraft, they will feel the gravity of Mars for the first time, about 1/3 of Earth's gravity. Their bodies will feel lighter, but their suits will be heavy. Before stepping outside, they must confirm that the life support systems, the airlock, and the suits are all functioning. Every seal must hold, every sensor must read correctly. The first person to set foot on Mars will likely descend a ladder from the habitat deck to the surface. Their boot will press into the red dust, and that footprint will remain there for millions of years because there is no wind or rain to erase it. That moment is not just a victory for the crew. It is the culmination of thousands of engineers, scientists, and visionaries who worked for decades to make it possible. The science objectives begin immediately. Soil samples are collected and analyzed for signs of past life. The atmosphere is tested for trace gases. Seismometers are deployed to detect Mars quarks and understand the planet's internal structure. But the primary objective is not just science, it is survival. The crew must prepare the habitat for long-term habitation. They will deploy solar panels, set up a communication array, and begin testing the ISRU equipment that will produce oxygen and water. Each day on the surface builds toward self-sufficiency. The cargo delivered with them includes spare parts, extra food, and tools for construction. Without a reliable surface base, return to Earth is impossible. The first landing proves that we can reach Mars safely. The next landing will prove we can stay there. A single footprint on Mars is historic. A permanent settlement is something else entirely. The first landing proves we can get there. The colony that follows proves we can stay. That transformation from temporary visitors to permanent residents is the 10th milestone, and it demands far more than just a habitable shelter. It requires building an entire small town from scratch on an alien world, with all the infrastructure, social structures, and economic activity needed to sustain human life indefinitely. The early colony will start small, likely as a pressurized habitat module delivered by the first crewed mission. That module is a metal tube buried under a layer of Martian soil for radiation shielding. Inside, 4 to 6 people live, work, sleep, and eat for their entire surface stay. Over the next few years, additional modules arrive from Earth, connected by airtight tunnels. Each new module adds space, a laboratory, a medical bay, a communal kitchen, a gymnasium. The colony grows room by room, like assembling a submarine on the surface of a desert world. Power comes first from solar arrays deployed across the flat plains near the habitat. Martian sunlight is weaker than on Earth, but the thin atmosphere means more high-energy photons reach the ground. Large fields of photovoltaic panels can generate enough electricity for basic needs. However, solar power is intermittent. Dust storms can block the sun for weeks. That is why the colony will also bring a nuclear fission reactor. A small, compact reactor buried safely underground provides constant, reliable power regardless of weather or time of day. The reactor uses uranium fuel and generates heat to turn a turbine, producing electricity around the clock. With both solar and nuclear, the colony has a robust energy grid that can handle the demands of life support, manufacturing, and farming. ISRU plants are the heartbeat of the colony. A machine the size of a shipping container sits outside the habitat, drawing in Martian air and extracting carbon dioxide. Another unit heats water ice mine from the ground and splits it into oxygen and hydrogen. Oxygen is stored for breathing and for rocket propellant. Hydrogen is combined with carbon dioxide to make methane fuel. These plants run day and night, building up a stockpile of resources that would otherwise have to be shipped from Earth at enormous cost. Every kilogram of oxygen produced locally is a kilogram that did not have to be launched from the home planet. The greenhouse is the most visible sign of life, under a transparent dome or inside a pressurized tunnel filled with LED lights. Rows of lettuce, tomatoes, potatoes, and strawberries grow in nutrient-rich water. The air smells like damp soil and fresh leaves, a stark contrast to the sterile, metallic scent of the habitat. Astronauts spend part of each day tending the plants, checking pH levels, harvesting ripe vegetables. The food supplements their prepackaged rations and provides essential vitamins. More importantly, the green space lifts their spirits. On a world where the horizon is orange and the sky is pink, a splash of green reminds them of home. Getting around the colony requires a fleet of rovers. Pressurized rovers allow crew members to travel tens of kilometers from the habitat without wearing suits. They can explore geological features, scout new mining locations, or simply drive to a hilltop for a view of the landscape. Unpressurized rovers, similar to open buggies, are used for short trips around the base. A network of cleared roads connects the habitat modules, the power plant, the ISRU facility, and the landing pad. Over time, a small transportation system emerges, like the paths between buildings in a remote scientific station on Earth. The psychological and social challenges of colony life are just as critical as the technical ones. A crew of 4 living in a cramped space for months can experience friction, boredom, and loneliness. The colony must be designed with privacy in mind. Each crew member has a personal quarters, a small room with a bed, a desk, and a screen for communication with family back on Earth. Common areas encourage social interaction: a dining table, a lounge with books and games, a window facing the Martian landscape. Recreation is important. There might be a virtual reality system for simulated hikes on Earth, or a small gym to stay fit in reduced gravity. The colony runs on a schedule that balances work, exercise, leisure, and sleep, mirroring the rhythms of a normal day. Governance in the early colony is simple. A commander makes operational decisions, while a medical officer handles health, and a mission scientist sets research priorities. As the colony grows, a more formal structure emerges. Residents elect representatives to a council that decides rules for resource allocation, waste management, and conflict resolution. The colony might adopt a form of direct democracy for major decisions, with all members voting on policies that affect everyone. Over time, a legal system develops based on international space law and the founding charter of the settlement. The goal is not to replicate any single government from Earth, but to create a system that is fair, transparent, and adaptive to the unique conditions of Mars. Population growth begins with the early pioneers, then expands as reliable transport reduces the cost and risk of sending more people. The original crew returns to Earth after their tour, but some may choose to stay for a second mission or even permanently. New arrivals include scientists, engineers, doctors, and eventually families. The colony needs a school, a clinic, and a small store. Economic activity starts with the export of scientific data and rare metals, but the real engine is self-sufficiency. Every new greenhouse, every new ISRU plant reduces dependence on Earth. The Mars Direct Plan, first proposed by Robert Zubrin in the 1990s, outlined a minimalist approach using existing technology to send a small crew to Mars with a return vehicle. That plan inspired many of the concepts now being developed. SpaceX has a far more ambitious vision, a city of 1 million people on Mars by the end of this century. That city would require thousands of Starship flights, massive underground aquifers, factories that produce bricks from regolith, and a local economy with its own currency and laws. It sounds like science fiction, but the first steps are already being taken. The colony that begins with a single habitat module is the seed from which that city will grow. This permanent settlement becomes the testbed for full planetary independence. Every system that keeps the colony alive is a candidate for eventual use on other worlds. The lessons learned about closed-loop life support, local resource extraction, and social cohesion will be applied to future outposts on the moons of Jupiter and Saturn. Mars is the proving ground. If we can build a thriving community on a cold, dry, radiation-blasted world, we can build one anywhere in the solar system. And once that colony stands on its own, the next milestone becomes urgent. How do we ensure that it can survive even if Earth goes silent? A colony that survives is one thing. A world that breathes is another. The permanent settlement on Mars proves we can live there, but it does not change the fact that the surface is still cold, dry, and nearly airless. Every breath of oxygen inside the habitat comes from machines or plants grown under artificial light. Every step outside requires a pressurized suit. That works for a small outpost, but for a population of thousands or millions, those constraints become a wall that limits growth. The 11th milestone looks beyond survival and toward transformation, terraforming Mars into a planet where humans can walk unprotected under an open sky. The goal of terraforming is to thicken the Martian atmosphere and raise its temperature until liquid water flows on the surface. That would allow crops to grow in open fields, eliminate the need for bulky spacesuits during outdoor work, and create a self-regulating climate system. The process is not fast. Most estimates put the timescale somewhere between several centuries and a few thousand years, far longer than any single human life. But it is the ultimate expression of our ability to reshape an entire world. Proposed methods fall into two broad categories: warming the planet and generating oxygen. Warming comes first because Mars is simply too cold for liquid water to exist at the surface for long. The average temperature hovers around -60 degrees Celsius, far below freezing. To raise it, you need to trap more solar heat. One method is to release powerful greenhouse gases into the atmosphere. Certain gases, like chlorofluorocarbons, are thousands of times more effective at trapping heat than carbon dioxide. On Earth, we try to reduce them because they damage the ozone layer. On Mars, that same property becomes an advantage. A small factory on the surface could produce CFCs from elements found in the soil and atmosphere, then vent them into the air. Over years, the concentration builds up and the planet warms. Another approach targets the frozen carbon dioxide at the poles. Mars has vast polar caps made mostly of dry ice, solid carbon dioxide. If you warm those caps by several degrees, the CO2 sublimates directly into gas, thickening the atmosphere and creating a runaway greenhouse effect. More atmosphere means more heat is trapped, which melts more dry ice, which thickens the atmosphere further. Some proposals suggest covering the polar caps with dark dust or soot to absorb more sunlight and accelerate the process. Others imagine placing giant orbital mirrors that reflect sunlight onto the poles, melting them faster. In theory, a small trigger could set off a chain reaction that transforms the thin atmosphere into something much denser. Once the atmosphere is thicker and the temperature rises, the next challenge is generating breathable oxygen. Mars has plenty of oxygen bound up in the carbon dioxide of the atmosphere and in the rust-colored minerals of the soil. To free that oxygen, you need living organisms. Genetically engineered bacteria could be seeded across the surface. These microbes would consume carbon dioxide and release oxygen through photosynthesis. Over centuries, they would convert a significant fraction of the atmosphere into breathable air. Mosses and lichens could follow, tough plants that can survive harsh conditions and build a thin layer of soil. Eventually, hardier grasses and shrubs would take root, and with each generation the oxygen levels rise. This is not as simple as spreading seeds. The low pressure of the early Martian atmosphere would cause liquid water to boil at body temperature, so any exposed plant must be adapted to extreme conditions. Genetic engineering offers a path. Scientists could splice genes from extremophiles, organisms that thrive in Earth's most hostile environments, into common plants to make them resistant to cold, drought, and radiation. The ethical debates around terraforming are as big as the engineering challenges. Do we have the right to alter an entire planet, especially if it harbors microbial life? The discovery of even primitive bacteria on Mars would raise profound questions. Some argue that any native life, no matter how simple, deserves preservation, and that altering the planet would destroy the one chance we have to study an independent origin of life. Others counter that a world without intelligent life belongs to the species that can use it, and that transforming Mars is a natural extension of human ingenuity and survival instinct. These debates will likely play out over decades as we learn more about the Martian subsurface and its potential for biology. But terraforming is not a prerequisite for colonization. The early settlers do not need to wait for the atmosphere to thicken. They can live in pressurized habitats and rovers, exactly as we have described in the previous milestones. The colony can grow for centuries inside those domes and tunnels, slowly building the infrastructure that will one day make terraforming possible. The process becomes a long-term project, like building a cathedral in medieval times. No one who lays the first stone will see the final spire, but they believe in the vision enough to start. That vision of a living, breathing Mars connects directly to the next frontier. The same resources that will warm the red planet, carbon, hydrogen, oxygen, and metals, are abundant in another part of the solar system, the asteroid belt. And while terraforming takes thousands of years, asteroid mining offers a much nearer reward that could fuel the expansion of our civilization across the solar system. A single metal-rich asteroid holds more platinum than has ever been mined on Earth. That fact is not a prediction. It is a measurement based on the composition of the millions of rocks drifting between Mars and Jupiter. These asteroids are not just obstacles to avoid. They are floating mines packed with water, iron, nickel, cobalt, and precious metals. The resources locked inside them could supply off-world industries for centuries and create a space-based economy that no longer relies entirely on the ground. The first step is prospecting. We have already sent robotic scouts to study a few of these objects up close. NASA OSIRIS-REx mission traveled to an asteroid named Bennu. It spent 2 years orbiting and mapping the surface before briefly touching down and collecting a sample. That sample, returned to Earth in 2023, revealed that Bennu is rich in carbon and water-bearing minerals. Japan's Hayabusa 2 did the same with the asteroid Ryugu. Its sample contained organic compounds and hydrated clay, exactly the kind of material that can be broken down into water and fuel. Both missions proved that asteroids are not dry, barren rocks. They are reservoirs waiting to be tapped. The easiest targets are near-Earth asteroids. These are objects whose orbits bring them close to our planet. They require less energy to reach than the main belt. A well-planned mission could send a small spacecraft to rendezvous with one, survey its composition, and begin extraction. The extraction itself depends on the type of asteroid. Carbonaceous chondrites are dark, loose aggregates rich in water and carbon. A simple method is to heat the material in a sealed container. The water vaporizes, then condenses into liquid. That water is pure and can be split into hydrogen and oxygen for rocket fuel. Metallic asteroids, composed largely of iron and nickel, are harder but more valuable. A single metallic asteroid a kilometer across could contain more iron than the entire global annual production. Mining them might involve drilling into the surface, melting the metal with focused sunlight, or using magnetic separation to pull out the valuable elements. Processing in orbit changes everything. Instead of hauling raw ore down to Earth, you refine it in space. A small factory attached to the asteroid spins up to create artificial gravity or uses zero-G techniques for separation. The metals are cast into structural beams, plates, and wiring, all without ever touching a planetary surface. Those components can be used to build space stations, fuel depots, and even the hulls of interplanetary spacecraft. The most immediate payoff is propellant. Water from asteroids can be electrolyzed into hydrogen and oxygen, the same propellant used in chemical rockets. A tanker filled with asteroid water could refuel a spacecraft in orbit for a fraction of the cost of launching that fuel from Earth. That refueling capability makes reusable rockets far more practical and reduces the number of launches needed for deep space missions. A single tanker mission to an asteroid could return enough water to refuel a dozen Mars-bound ships. The economic implications are staggering. At current prices, a platinum-rich asteroid 200 meters wide could be worth several $1 trillion. But the real value is not in bringing that metal to Earth, which would crash the market. The value is in using those materials in space, where every kilogram launched from the ground costs thousands of dollars. A beam manufactured from asteroid metal is essentially free once the mining infrastructure is in place. That low-cost material enables the construction of habitats, solar power satellites, and orbital shipyards on a scale impossible with Earth-sourced supplies. Companies like Planetary Resources and Deep Space Industries, though no longer operating, laid the groundwork. Today, NASA and the European Space Agency continue to fund prospecting missions and resource mapping. Private startups are re-emerging with new ideas for small, automated miners that can attach to an asteroid and begin extraction within a few years. The technology is not science fiction. It is engineering that we are beginning to build. The first successful asteroid mining mission will mark the moment humanity becomes a spacefaring industrial civilization. It will prove that the solar system is not a barren wilderness but a vast supply chain waiting to be activated. And with that supply chain established, the next logical step is to build permanent factories and assembly yards in orbit, places where raw asteroid metal is turned into the ships, habitats, and infrastructure that will carry humanity to the outer planets. A ship built in space never has to fight gravity. On Earth, every rocket is a carefully sculpted cylinder designed to survive the crushing pressure of ascent. Its shape is a compromise between aerodynamics and strength, but once you move the factory into orbit, that compromise disappears. In the vacuum of microgravity, you can build structures that would collapse under their own weight on the ground. You can stretch solar arrays the size of football fields. You can assemble trusses longer than skyscrapers, and you can do it all without ever worrying about how to fit the finished product inside a rocket fairing. This is the promise of orbital shipyards, the factories that will build the infrastructure for a multi-planetary civilization. The key advantage of zero-gravity manufacturing is that it removes the single largest constraint on spacecraft design, the launch vehicle. Every satellite or station module sent up from Earth must be folded into a nose cone. Its diameter is limited by the rocket's width. Its length is limited by the fairing's height. But a ship assembled in orbit has no such limits. You can bring up components in multiple launches, then join them together like a giant Lego set. The finished vehicle can be 10, 50, or 100 meters across because each piece only needs to fit inside the cargo hold of a single rocket. That opens the door to spacecraft that are not just larger, but fundamentally different in how they are built. Microgravity also changes the materials you can use. On Earth, molten metal sinks and separates by density, making certain alloys impossible to cast evenly. In space, surface tension and capillary action dominate. Metals mix without settling. That allows for alloys that are lighter, stronger, or more conductive than anything produced on the ground. For example, a composite of aluminum and tungsten, normally impossible because tungsten is much denser and would sink to the bottom of a casting mold, can be formed into a uniform block in orbit. That block might become a radiation shield or a heat sink for a nuclear reactor. Foams can be created by injecting gas into molten metal in zero-G, producing ultra-lightweight structural panels with incredible strength-to-weight ratios. Crystal growth benefits too. Semiconductors grown in microgravity have fewer defects and higher purity, which could lead to more efficient solar cells and computer chips. These materials are not just curiosities, they are essential for building the next generation of deep space hardware. Assembly in orbit will be done by a combination of human-operated telerobotics and autonomous machines. A robotic arm controlled by an operator on a nearby station or even from Earth with a slight time delay will move beams into position. Welding torches and fasteners will join them. 3D printers will extrude layers of molten metal into complex shapes, creating brackets, fuel tanks, and structural nodes on demand. The raw material comes from asteroid mining missions that deliver processed metal ingots and water ice to a depot near the shipyard. A single printer could consume a ton of regolith-derived feedstock and produce a pressure vessel for a habitat module without any human intervention. Over time, the shipyard becomes a self-replicating system. It builds its own robotic tools, its own storage containers, and eventually new shipyards to break free from Earth's supply chain. The first orbital shipyard will likely be small, attached to a commercial space station like the ones Axiom Space plans to launch. Axiom's modules will dock with the International Space Station initially, then separate to form an independent outpost. That outpost can include a small manufacturing bay where experiments test 3D printing and alloy production in microgravity. NASA Lunar Gateway, a small orbiting outpost around the Moon, will also serve as a testbed for assembly techniques. Astronauts on the Gateway will use robotic arms to attach new modules and repair scientific instruments. Every successful operation teaches engineers how to scale the process. The next step is a dedicated free-flying shipyard, a structure that contains docking ports, storage racks, robotic manipulators, and a pressurized workshop. It orbits in a high-traffic zone, perhaps in low Earth orbit near the International Space Station, or in a stable orbit between Earth and the Moon known as a Lagrange point. That location gives it access to both Earth-launched cargo and asteroid mining deliveries. Once the shipyard is operational, the pace of construction accelerates. A Mars transfer vehicle that would have required a decade of ground assembly and a single super-heavy rocket can now be built in orbit over a few months. Its components arrive as separate payloads: the crew capsule, the propulsion stage, the solar arrays, the cargo containers. The shipyard assembles them into a single spacecraft, tests its systems, and then tugs it into a departure orbit. That same shipyard can also build fuel depots, communication relays, and space stations for the outer solar system. It becomes the central hub of a growing industrial network. And the power required to run all those furnaces, printers, robots, and life support systems is enormous. A shipyard in constant operation needs a steady supply of electricity measured in megawatts. Solar panels that size would be massive, fragile, and vulnerable to eclipse. The logical next step is a dedicated power station that can supply that energy day and night, independent of the sun. The same factories that build spacecraft will soon need to build power plants capable of running the entire orbital economy. A solar panel in geostationary orbit catches sunlight 24 hours a day with no clouds, no night, and no atmosphere to dim it. That simple fact changes everything about how we think about energy. On Earth, solar power is intermittent. The sun sets every evening, clouds roll in, and seasons shift the angle of the light. Even in the sunniest deserts, a solar farm only produces electricity about a quarter of the time. But in space, the sun never sets. A large enough array in the right orbit can collect sunlight almost continuously, then beam that energy down to the surface whenever it is needed. This is space-based solar power, and it is one of the most transformative milestones on the path to a multi-planetary species. The technology is elegant in concept. You build a massive photovoltaic array in orbit, typically in geostationary orbit about 36,000 kilometers above the equator. At that altitude, the satellite stays fixed over one point on the ground. The array converts sunlight into electricity. Then that electricity drives a transmitter that converts the power into a focused beam of microwaves or laser light. The beam travels through the atmosphere to a receiving station on Earth called a rectina, short for rectifying antenna. The rectina converts the microwave energy back into electricity and feeds it into the power grid. The whole process, from sunlight to beamed energy to usable power, happens in a fraction of a second. The advantages over ground-based solar are enormous. In space, sunlight is about 10 times more intense than the average sunlight that reaches the surface after filtering through the atmosphere. There is no weather, no atmospheric absorption, and no nighttime. A single space solar satellite could deliver gigawatts of power continuously, enough to power a small city. And because the beam is directed, that power can be sent exactly where it is needed, to a disaster zone, a remote mining operation, or a growing colony on the moon. For lunar bases, the value is immediate. The moon has a 14-day night cycle. Solar panels on the surface go dark for 2 weeks at a time, forcing bases to rely on batteries or nuclear reactors. But a power satellite in lunar orbit can beam energy to the surface continuously. The rectina on the moon is just a lightweight mesh that can be unrolled across the regolith. It does not need to be aimed precisely, and it can power Habitat's rovers and ISRU plants through the entire lunar night. That means a lunar base no longer needs to haul heavy nuclear reactors or massive battery banks from Earth. A single orbiting power station can support the entire outpost. On Mars, the same idea works, but with an important twist. Mars receives less sunlight than Earth because it is farther from the sun. But a space-based power station in aerostationary orbit, the Martian version of geostationary orbit, can collect that weaker sunlight continuously and beam it down to the surface. During dust storms that blanket the planet for weeks, a power satellite becomes a lifeline. The ground-based solar arrays are choked with dust, but the satellite above the storm still sees clear skies. The colony stays powered and warm while the surface waits for the dust to settle. Building these satellites is the hard part that the previous milestone solves. An orbital shipyard assembles the massive arrays piece by piece. The photovoltaic panels are manufactured from asteroid-derived silicon, or from advanced thin film materials that are lighter and more efficient than anything produced on Earth. The transmitter dish, potentially hundreds of meters across, is constructed from lightweight trusses assembled by robotic arms. The raw materials come from Asteroid Mining, and the factory runs on power from an early demonstration satellite that proves the concept. The first space solar satellite will likely be small, a few hundred kilowatts, just enough to power a lunar base camp. But once the technology is proven, the scale grows rapidly. The cost challenge is real. Launching the components for a gigawatt-scale power satellite using current rockets would be prohibitively expensive. But as reusable launch systems and orbital manufacturing reduce the price per kilogram, the economics shift. A single space solar satellite might cost tens of billions to build and deploy, but it produces power for decades with no fuel cost and minimal maintenance. Over its lifetime, the cost per kilowatt-hour can compete with ground-based solar and nuclear, especially in remote or off-world locations where fuel resupply from Earth is expensive or impossible. Safety is a concern that engineers take seriously. The microwave beam is designed to be low intensity, comparable to the power density of sunlight at noon. Birds flying through the beam experience no harm. Aircraft can be rerouted around the transmission zone. The retina on the ground includes safety systems that shut down the beam instantly if something goes wrong. Laser-based designs use infrared wavelengths that are invisible but also fail-safe. The technology has been tested in labs and small-scale demonstrations. Japan's JAXA agency successfully beamed a few kilowatts of power wirelessly over a distance of 50 meters in a test facility, and later transmitted power from a ground station to a small receiver on a moving vehicle. The principles are proven. Scaling them up is an engineering challenge, not a physics problem. The strategic value of space-based solar power goes beyond clean energy on Earth. It creates a power grid that is independent of planetary surfaces. A network of power satellites can beam energy to spacecraft, to orbital depots, and to colonies across the solar system. A ship traveling to Jupiter can refuel its batteries by receiving a beam from a power satellite along the way. A base on the Moon can sell excess power back to Earth, creating the first interplanetary energy market. Energy independence from Earth is the foundation of a true multi-planetary civilization, and once that power grid is humming, the next bottleneck becomes clear. All those colonies, ships, and satellites need to talk to each other. The flow of data across millions of kilometers will require a communication network that can handle the delay, the interference, and the sheer volume of information a growing civilization demands. That is the milestone that will link every world into a single conversation. A radio signal takes up to 20 minutes to reach Mars from Earth. That delay makes a simple conversation impossible. You ask a question, then wait 40 minutes for a reply. The sense of isolation is profound, and for a colony trying to coordinate with the home world, it is a fundamental constraint on what is possible. The answer is not to eliminate the delay, because physics will not allow that, but to build a network that can handle it gracefully. A communication system designed from the start for the vast distances and long gaps of interplanetary travel. This is the Interplanetary Internet, and it is the nervous system of any multi-planetary civilization. The first layer of that network is a constellation of relay satellites. Around Mars, a small fleet of orbiters will serve as data highways. Each satellite carries a set of antennas, some pointed toward the surface to talk to rovers and habitat bases, others pointed toward deep space to link with Earth. These orbiters are positioned so that at least one is always in line of sight with the surface, even when Mars rotates the colony away from Earth. The same logic applies at the Moon. A lunar communications relay in orbit around the Moon ensures that bases on the far side can stay connected to Earth without the blackout that occurs during a direct line of sight pass. For the actual data link, the backbone of the network will shift from radio to laser communication. Lasers pack far more information into each beam because light waves have a much higher frequency than radio waves. A laser terminal the size of a shoebox can transmit gigabits per second across millions of kilometers. That is fast enough to stream high-definition video from the surface of Mars, to send detailed medical scans back to Earth for a doctor to review, or to update the digital maps of the colony in real time. NASA tested this technology with the Lunar Laser Communication Demonstration, which sent data from the Moon to Earth at speeds comparable to a home internet connection. The next step is to build laser terminals into every major spacecraft and habitat, creating a mesh network that routes data automatically. But a standard internet protocol like the one used on Earth assumes that every packet of data will arrive in a reasonable time. On interplanetary distances, that assumption breaks down. The solution is a protocol called Delay or Disruption Tolerant Networking, or DTN for short. Instead of expecting immediate delivery, DTN stores each packet at a node along the path until the next link becomes available. Think of it like a relay mail service. You hand a letter to a courier who carries it to the next town, then hands it to the next courier, and so on until it reaches the destination. If a satellite goes behind a planet for a while, the data waits patiently. When the connection reappears, the data resumes its journey. This store and forward method makes the network resilient to the long gaps and occasional interruptions that are inevitable in space. With this network in place, remote control of robots and scientific instruments becomes practical. A rover on Mars might be operated with a time delay, but the commands are sent as a sequence of instructions that the rover carries out autonomously. The network sends back status updates and images, allowing engineers on Earth to adjust the plan for the next day. That same link enables telemedicine. A crew member on the Moon or Mars can have their vital signs streamed to a doctor on Earth, who can review high-resolution images and give guidance during surgery or an emergency. The colony is not truly isolated because the network keeps a thread of expert knowledge always within reach. Social connection is just as important. Video calls with family, recorded messages that arrive after a delay, shared photos of daily life. These are the threads that keep a far-off colony tethered to the human community. Boredom and loneliness are serious risks on long missions, and the ability to maintain ties with loved ones back home is a psychological lifeline. The network also carries news, entertainment, educational content, and updates from the global community. It makes Mars feel less like a prison and more like a distant neighborhood. The existing deep space network run by NASA is a collection of giant radio dishes spread across 3 continents on Earth. It has supported every major deep space mission for decades, but it is not designed for the scale of a permanent colony. The network needs upgrades, more dishes, more laser terminals, and automated scheduling that can handle hundreds of simultaneous connections instead of just a few. Private companies are entering this space as well, proposing commercial interplanetary communication services that would sell bandwidth to governments and settlers alike. This unified communication network is the thread that ties every outpost together. Without it, each colony is a silo cut off from the knowledge and support of Earth. With it, the civilization becomes a single conversation, a slow conversation, but a connected one. And as that conversation hums across millions of kilometers, the next problem becomes impossible to ignore. All those colonies, ships, and habitats spin inside the grip of different gravitational fields, and the way we move between those fields dictates how fast the network can expand. The human body evolved under a constant pull of gravity, and without it, things start to break down. After just a few months in microgravity, bones lose calcium, muscles atrophy, and fluids shift upward, putting pressure on the eyes and altering vision. Astronauts on the International Space Station exercise vigorously for 2 hours every day just to slow the damage, but they cannot stop it completely. On a 6-month trip to Mars, the effects would be serious. On a multi-year voyage to the outer planets, they could become debilitating or even fatal. That is why artificial gravity is not a luxury. It is a medical requirement for any civilization that plans to live and travel far from Earth for extended periods. The most practical way to create artificial gravity is through rotation. Spin a spacecraft or a habitat, and the centrifugal force pushes everything outward, creating a simulated gravity that feels like the real thing. The faster the spin, the stronger the force. The larger the radius, the more comfortable the ride. A small radius with high spin can cause disorientation because your head moves faster than your feet, creating a noticeable Coriolis effect that makes you feel like you are tilting when you turn. A large radius with slower spin feels much more natural. Early Mars transfer vehicles might include a rotating section, perhaps a ring that spins independently from the rest of the ship. The crew would live and sleep in that ring, then move to the zero-G center for experiments or propulsion work. The ring would be about 30 meters in diameter, spinning at a few rotations per minute to produce Earth normal gravity at the outer edge. That is enough to keep bones strong and heart function normal during the months of transit. The challenge is mechanical. A rotating ring requires bearings, seals, and power transfer systems that work reliably over years of use. Any imbalance could cause wobbles that stress the structure, but the engineering is well understood from designs proposed by NASA and von Braun back in the 1950s. Modern materials and robotics make it far more feasible. For permanent space colonies, the vision grows much larger. The O'Neill cylinder, named after physicist Gerard O'Neill, is a rotating space habitat tens of kilometers long and several kilometers in diameter. The interior surfaces are landscaped with valleys, lakes, and towns, all held against the inner wall by centrifugal force. The sun is simulated by mirrors and light pipes that channel sunlight from outside. The rotation creates a gravity gradient from full Earth gravity at the outer rim to near zero at the central axis. That allows for a range of activities, from swimming in 0G to farming in 1G. An O'Neill cylinder could house millions of people in a self-contained world. It would be built from materials mined from the Moon or asteroids, assembled in orbit by robotic factories. The cost is enormous, but the payoff is a permanent home that does not depend on any single planet. Partial gravity adds another layer of complexity. The Moon has 1/6 Earth gravity. Mars has 1/3. No one knows for sure what the long-term health effects of living in those conditions will be. Studies on Earth use bed rest or centrifuges to simulate reduced gravity, but the real data will come from actual colonies. It is possible that the human body can adapt to Martian gravity without serious harm, allowing colonists to live there their entire lives. It is also possible that children born on Mars would never be able to travel to Earth because their bodies would not withstand the higher gravity. Research on lunar and Martian gravity will guide the design of rotating habitats for transit and for colonies in low-gravity environments. A space station at a Lagrange point might rotate to provide Earth normal gravity for crew who spend months there, while ships to Jupiter might rotate at partial G to match the gravity of their destination. This milestone ensures that humans are not limited to the surface of one planet. With artificial gravity, we can build homes in orbit, on moons, and in transit between worlds. The body stays healthy, the mind stays sharp, and the journey becomes a place to live, not just a passage to endure. And once the crew arrives and settles into a new home, the next challenge is keeping that home alive without constant resupply from Earth. That leads directly to the need for a self-contained bubble of life, a biosphere that recycles everything and wastes nothing. Getting water from ice is one thing. Having a system that breathes, eats, and cleans itself is another. A Mars colony that relies on machines to recycle air and water can survive for years, but it remains dependent on spare parts and consumables shipped from Earth. The real leap happens when the colony becomes a living organism, a closed ecological system where microbes, plants, and animals work together to keep everything in balance without any external inputs. That is the fully self-sustaining biosphere, and it represents the point where a Martian settlement truly cuts the umbilical cord to the home world. The idea was tested on a grand scale in the early 1990s with a project called Biosphere 2. In the Arizona desert, a massive sealed glass and steel structure was built to house 8 people and several miniature ecosystems, including a rainforest, an ocean, a desert, and agricultural areas. The goal was to see if a closed loop could support human life without any exchange of materials with the outside world. The results were humbling. Oxygen levels dropped dangerously low because microbes in the soil consumed oxygen faster than plants could produce it. Carbon dioxide levels fluctuated wildly, and nitrous oxide built up to levels that affected the crew's health. The agricultural systems struggled to produce enough food, and the crew lost weight. The experiment was eventually opened to the outside, revealing that a fully closed system is far more complex than anyone had imagined. But the lessons from Biosphere 2 were invaluable. Engineers learned that a self-sustaining biosphere cannot rely on simple mechanical recycling. It needs a diverse web of life. Microbes are the invisible workhorses. They break down waste, fix nitrogen, and recycle nutrients that plants need. Without a healthy microbial community, the system stalls. Plants are the next layer. They produce oxygen, absorb carbon dioxide, and generate food. But a single crop monoculture is fragile. If a disease strikes the lettuce, the whole food supply collapses. That is why a biosphere must include multiple plant species, each with different roles. Legumes fix nitrogen in the soil. Grains provide carbohydrates. Leafy greens supply vitamins. Fruit trees offer variety and long-term resilience. Beyond plants, the system also needs animals, not cows or pigs, but smaller creatures like fish, insects, and perhaps chickens. Fish in aquaculture tanks can be fed with plant scraps, and their waste becomes fertilizer for the hydroponic beds. Insects like crickets or mealworms can be raised efficiently as a source of protein, requiring far less space and water than traditional livestock. Chickens provide eggs and meat on a smaller scale, and their droppings can be composted into the soil beds. Every organism in the biosphere has a role, and the waste of one becomes the resource of another. The colony becomes a miniature version of Earth's own biosphere, where nothing is wasted and everything cycles. The integration with life support is seamless. The air that the crew breathes out, rich in carbon dioxide, is piped into the greenhouse where plants use it for photosynthesis. The oxygen they produce returns to the habitat. Water from the crew's sinks, showers, and toilets is filtered through a combination of mechanical purification and biological treatment, including constructed wetlands where microbes and plants absorb nutrients. The clean water is then used again for drinking, washing, and irrigation. Even human solid waste is processed, either through composting or through a bioreactor that breaks it down into safe organic matter for soil. Over time, the colony reaches a point where the only external input is sunlight or artificial light from a nuclear or solar power source. Everything else is recycled, regenerated, and reused. Resupply from Earth becomes a luxury, not a necessity. Achieving this level of closure is a monumental engineering challenge. The system must be robust enough to handle emergencies, like a crop failure or a pump breakdown. Redundancy is built in. If the hydroponic system fails, there is a backup supply of stored food. If the biological water filter stops working, a mechanical filter takes over. The crew must be trained to monitor dozens of parameters, from pH levels in the aquaculture tanks to the concentration of trace gases in the air. But once the biosphere stabilizes, it runs with a life of its own. The plants grow, the fish spawn, the microbes thrive, and the crew lives inside a self-sustaining world of their own making. That milestone also marks a profound psychological shift. The colony is no longer a precarious outpost. It is a permanent home. The risk of a catastrophic failure that requires evacuation to Earth drops dramatically because the colony can weather supply disruptions. The next generation of Martians, those born on the Red Planet, will grow up knowing that their world can provide for them as long as the biosphere is respected and maintained. This self-sufficiency is the foundation for expansion to other worlds. If a biosphere works on Mars, it can work in an orbital habitat on a moon of Jupiter or inside a generation ship bound for another star. And with that independence comes a new responsibility, the risk of contaminating the pristine environments we find. The next milestone is learning how to explore other worlds without destroying the very signs of life we came to find. The biosphere thrives because every resource cycles in a closed loop, but the boundary between that artificial world and the alien landscape outside is not just a wall of metal and regolith. It is a line of biological trust. On Mars, the soil and air have been isolated from Earth life for billions of years. Any microbe that hitches a ride on a spacecraft or leaks from a habitat could spread into that pristine environment, disrupting any native ecosystem that might exist. And the danger runs both ways. A Martian microbe, if it exists, could be carried back to Earth inside a sample container or on a spacesuit, with consequences no one can predict. That is why planetary protection is not a bureaucratic checkbox. It is a scientific and ethical safeguard for every world we touch. The protocols begin long before launch. Every spacecraft destined for Mars or the Moon is assembled in clean rooms where technicians wear full-body bunny suits and the air is filtered to remove nearly all particles. Components are sterilized using heat, radiation, or chemical vapors to kill any lingering spores. The goal is to reduce the number of viable microbes on the hardware to a vanishingly low level, often fewer than 300,000 spores per square meter. For missions that will land in regions considered special, such as the Martian polar caps or areas where liquid water might exist, the requirements are even stricter. The spacecraft is heated to temperatures that would destroy almost all life forms, leaving behind an extremely clean surface. Once the colony is established, those standards do not relax. Every piece of equipment that leaves the habitat must be decontaminated before entering the Martian environment. Airlocks act as biological barriers. Suits are cleaned and inspected after every excursion. Waste from the colony, including human waste, is processed inside the closed-loop biosphere and never released into the open air. The colony is a sealed bubble, not just to protect the settlers but to protect Mars from them. The reverse flow is equally important. Samples of Martian rock and soil that are returned to Earth will be treated as potentially hazardous. They will be sealed in multiple layers of containment and transported in specialized containers designed to survive a launch failure or an off-nominal entry. The receiving facility on Earth will be a Biosafety Level 4 equivalent lab, the highest level of containment with negative air pressure, full body suits with independent air supplies, and rigorous decontamination procedures. Every core sample will be studied in isolation until scientists are certain it contains nothing dangerous. This caution is not paranoia. History on Earth shows what happens when a new microbe jumps from one host to another. The transfer between worlds could be far more disruptive because neither side has immunity or defense. the ethical dimension is just as profound. If Mars has its own life, even if it is only simple bacteria buried deep in the permafrost, that life represents a second genesis, an independent origin of biology. To contaminate it with Earth organisms would be to erase the one thing that makes Mars scientifically priceless. We would lose the chance to study a truly alien form of life, and we would become the agents of its destruction. That is why some scientists argue that certain regions of Mars, such as the subsurface where water might support life, should be designated as protected zones where human activity is limited or banned entirely. The idea of terraforming takes on new weight in this context. Melting the polar caps and thickening the atmosphere would radically alter the Martian environment, potentially wiping out any native organisms that might be adapted to those cold, dry conditions. The decision to terraform is not just an engineering choice, it is a moral one. We must first understand what we are building on top of. That requires decades of careful exploration, sample analysis, and robotic reconnaissance before we commit to planetary-scale change. This milestone forces us to slow down and think. It says that expanding to other planets must be done responsibly, that the drive to settle should not override the duty to preserve and study. That sense of responsibility naturally extends to how we govern ourselves across multiple worlds. A colony on Mars cannot operate under the same rules as a research station in Antarctica. It needs laws, agreements, and a framework that balances the interests of the settlers, the scientific community, and the people of Earth. The next milestone is the creation of that governing system, the legal and political architecture that will ensure a multi-planetary civilization is stable, fair, and sustainable. A single set of rules cannot govern a civilization that spans two worlds. The moment the first colony on Mars becomes permanent, the old agreements between nations on Earth will no longer be enough. Who owns the land a settler builds on? Who controls the water ice beneath the surface? If a dispute arises between a Martian habitat and a mining company from Earth, which court has the final say? These questions are not abstract. They will be asked within the first few years of settlement, and unless a clear framework exists, the answers will be decided by whoever has the most leverage. That is a recipe for fragmentation and conflict. The foundation of space law today is the Outer Space Treaty, signed in 1967 and now ratified by over 100 countries. Its core principle is that space, including the Moon and other celestial bodies, belongs to no one. No nation can claim sovereignty. No country can plant a flag and declare territory. Weapons of mass destruction are banned from orbit. All activities must be carried out for the benefit of all humankind. For the era of robotic probes and short-term missions, that treaty was sufficient. But for a permanent colony with its own economy and citizens, it leaves enormous gaps. There is no provision for private property rights. If a company builds a habitat on Mars, does it own the structure and the ground beneath it? The treaty says no nation can claim territory, but it does not clearly address individual or corporate ownership. That ambiguity creates risk. Without clear property rights, investors are reluctant to fund the enormous cost of building a lunar base or a Martian greenhouse. They need to know that their investment will be protected and that someone else cannot simply take over their facility. The Artemis Accords, signed in 2020 by the United States and later joined by several other nations, attempt to fill some of these gaps. They affirm that extraction of resources from the Moon or asteroids is allowed, as long as it is done in a way that respects the Outer Space Treaty. They also establish safety zones around operational sites to prevent harmful interference. The Accords are a step forward, but they are not a binding global treaty. They are a set of bilateral agreements between like-minded countries. Not all spacefaring nations have signed. China and Russia have not. Without a broader consensus, the legal landscape remains patchy. different colonies might operate under different rules depending on which flag their sponsoring nation flies. That patchwork can work for a while, but as populations grow and trade increases, the need for a unified legal system becomes urgent. The colony itself will need a form of self-governance. Early settlers cannot govern by committee from Earth because the 20-minute communication delay makes real-time oversight impossible. Decisions about daily life, resource allocation, and dispute resolution must be made on Mars. The first governing model might be a simple council elected by the settlers, with a charter that defines basic rights and responsibilities. That charter would likely draw from the principles of the Outer Space Treaty, but adapt them to the realities of a closed environment where every resource is precious. For example, water is shared property on Mars. No one can hoard it, but the user of a greenhouse might have priority rights to a certain allocation as long as they use it productively. Property rights on another world will not look like Earth's. On Earth, land is valuable because it is scarce and fixed. On Mars, land is abundant at first, but habitable, shielded, and pressurized space is not. So ownership might be more like a lease from the colony government, combined with the right to use a specific area for a defined purpose. Intellectual property also needs a new framework. If a scientist on Mars discovers a new drug that only works in reduced gravity, who owns the patent? The scientist, the colony, the Earth-based corporation that funded the research. Without clear rules, disputes can slow innovation. Conflict resolution is perhaps the most sensitive area. A violent crime on a spacecraft or colony is a rare but possible event. The Outer Space Treaty says that astronauts are envoys of humankind, and that jurisdiction remains with the nation of registry of their spacecraft or habitat. But on Mars, multiple habitats from different nations might be clustered together. A crime could involve citizens of different countries. An international agreement on criminal jurisdiction, similar to the conventions that govern the International Space Station, will need to be expanded for permanent settlements. Some legal scholars propose a form of mediated arbitration for civil disputes, where a neutral panel drawn from both Earth and Mars hears cases and issues binding decisions. Over time, a body of precedent will build up, forming a common law of space. The relationship between Earth and Mars will evolve as the colony matures. In the early years, Mars is dependent on Earth for everything, so Earth holds the power. But as the colony becomes self-sufficient, that balance shifts. The colony might demand more autonomy in setting its own laws, taxes, and trade policies. A Martian assembly could be formed, separate from the Earth-based space agencies, with real authority over internal affairs. Earth governments might resist, but the logic of distance and self-sufficiency is inexorable. A stable multi-planetary civilization requires that each world have a voice in its own governance, and that the rules binding them together are based on consent, not coercion. This entire legal evolution must be guided by the principle that space resources belong to no single nation but to all of humanity, while respecting the rights and freedoms of those who risk everything to build a new home. Without that balance, the dream of a multi-planetary species becomes a source of conflict rather than cooperation. And once the legal foundations are laid, attention must turn to the engine that drives any society, the economy. Trade flows, currencies, and markets will determine how fast the civilization grows, and that is the next milestone on the road to the stars. The first cargo shipment from an asteroid will be worth more than all the gold ever mined on Earth. That single container of platinum group metals, refined in zero gravity and dropped gently into a waiting orbital depot, will mark the birth of an interplanetary economy. Until that moment, every colony and outpost exists as a cost center, dependent on subsidies and government funding from the home world. But trade changes the equation. It turns space into a place where value is created, not just consumed. the earliest trade goods will be the most basic and essential. Water ice from the lunar poles or from carbonaceous asteroids can be split into hydrogen and oxygen. That propellant is the currency of the solar system. A tanker full of water delivered to a fuel depot in low Earth orbit is worth its weight in launch costs saved. A single asteroid miner could supply enough water to refuel a dozen Mars-bound ships, and the savings in launch mass from Earth are measured in hundreds of millions of dollars. Water is the first commodity, the oil of the early space economy. Metals follow closely. Iron, nickel, and cobalt from metallic asteroids can be processed into structural beams, pressure vessels, and shielding. On Earth, those materials cost money to mine, refine, and transport. In space, they are essentially free once the extraction infrastructure is built. A kilogram of steel delivered to a lunar base from Earth carries a price tag of tens of thousands of dollars. A kilogram of asteroid-derived steel delivered to the same base costs only the energy and labor to process it. That gap drives the entire business case for asteroid mining. The first customers will be orbital shipyards and lunar habitats, hungry for construction materials that do not have to be launched from Earth. Rare minerals and platinum group metals are the high-value cargo that makes early missions profitable. A single small asteroid a few hundred meters across could contain more platinum than has been mined in all of human history. But bringing that metal down to Earth would crash the market. The real value is in using it for in-space manufacturing. Platinum is a critical catalyst for fuel cells and chemical processes. It is also used in high-performance electronics. A factory in orbit that refines platinum from asteroid ore can supply the growing industrial base without ever needing to land on Earth. The profits come from selling to other space-based customers, not from returning to the home planet. Pharmaceuticals manufactured in microgravity represent another lucrative trade. Protein crystals grown in zero gravity can be larger and more perfectly ordered than any produced on Earth. Those crystals are essential for developing new drugs. The same microgravity environment allows for the production of certain medicines that are difficult or impossible to make in a gravity well. A small orbital pharmaceutical lab could produce a single batch of a rare drug worth millions of dollars. The raw ingredients are shipped up in small quantities, and the finished product is returned to Earth for distribution. The profit margin is enormous, and the market is guaranteed as long as humans on Earth need advanced medicine. Specialized components like optics, semiconductors, and fiber optics will also flow between worlds. The vacuum of space is naturally clean, and microgravity allows for perfect mixing of alloys and dopants. A chip fab in orbit could produce processors that are faster and more efficient than any made on Earth. Those chips would be essential for the computers that run the colony, the navigation systems of deep spaceships, and the artificial intelligence that manages the closed-loop biosphere. The trade in high-end components becomes a steady revenue stream that supports the entire space economy. Currency in this interplanetary market cannot rely on physical cash or a single national sovereign. Digital currencies, often built on blockchain technology, offer a natural solution. A transaction between a lunar water miner and a Mars habitat can be recorded instantly in a distributed ledger, even if the actual settlement takes hours or days due to communication delays. Smart contracts can automate payments when a tanker arrives at the depot or when a batch of pharmaceuticals passes quality inspection. The exchange rate between a Mars-based digital credit and an Earth-based dollar will fluctuate based on supply, demand, and the cost of shipping goods between the two worlds. Over time, a basket of commodities might back the interplanetary currency, giving it a stability that no single planet can provide. A thriving space economy does more than just pay for itself. It creates incentives for further expansion. When water from an asteroid can be sold to a fuel depot, and that fuel depot enables a cheaper trip to Mars, and Mars produces rare metals that can be sold back to Earth. The whole system becomes a self-reinforcing loop. Each new colony becomes both a producer and a consumer. The growth of the economy funds the development of new technologies, which lower costs further, which open up new markets. This is the engine that drives a multi-planetary civilization beyond the initial pioneering phase. It is the same dynamic that drove the age of sail, the railroad boom, and the rise of global trade on Earth. The only difference is the scale. The immediate effect of that economic engine will be a demand for faster, cheaper transportation. As trade volumes grow, the cost of moving cargo between worlds becomes the single largest bottleneck. That pressure will push engineers to develop the next generation of propulsion, systems that can move tons of material between Earth, the Moon, and Mars in weeks instead of months, and for a fraction of the current cost. The economy will not wait for slow rockets. It will demand a leap forward, and that leap is already taking shape in the form of advanced propulsion technologies that promise to shrink the solar system and make interplanetary trade routine. A fusion rocket would turn a trip to Jupiter from years into weeks. That is not a distant fantasy. It is an engineering target that several private companies and government labs are actively pursuing. The basic idea is simple. Instead of burning chemical fuel or using a fission reactor to heat propellant, a fusion engine would harness the same reaction that powers the sun. Two light atomic nuclei, usually isotopes of hydrogen, are forced together at extreme temperatures until they fuse into a heavier element, releasing a tremendous burst of energy. That energy can then be used to heat a propellant like hydrogen to enormous temperatures, creating a high-speed exhaust that produces thrust far more efficiently than any chemical or nuclear thermal rocket. The specific impulse of a fusion rocket could be 10 to 20 times higher than the best chemical engines. That means a spacecraft could carry the same propellant mass but travel much farther or much faster. A crewed mission to Saturn, which currently would take 8 years using chemical propulsion, could be completed in under a year. Regular cargo shipments between Earth and the asteroid belt would become routine, opening the entire inner solar system to commerce and settlement. The status of fusion research today is promising but not yet ready for spaceflight. Magnetic confinement designs like tokamaks and stellarators have made steady progress on Earth, with the International ITER project aiming for a net energy gain by the late 2030s. But those machines are the size of buildings and not suitable for a rocket engine. The breakthrough will come from compact fusion concepts. Private ventures like Helion Energy and TA Technologies are working on designs that are smaller, simpler, and potentially cheap enough to fly. Helion claims its reactor could produce net electricity by the late 2020s, and that a version adapted for propulsion could follow. Other approaches, like inertial confinement fusion using powerful lasers, have also shown progress in laboratory tests. A fusion drive would not just speed up travel within the solar system, it would make the outer planets truly accessible. The moons of Jupiter and Saturn, especially Europa and Enceladus, are believed to harbor subsurface oceans that could support life. Getting there with current technology requires long, expensive missions or gravity assists that take decades. With fusion, a probe could reach Europa in under 2 years. A crewed outpost on Titan, Saturn's largest moon, becomes a realistic goal for the second half of this century. The energy density of fusion fuel is so high that a single kilogram of deuterium and helium-3 could provide the same energy as thousands of tons of chemical propellant. That changes the economics of deep space exploration entirely. Beyond fusion, even more speculative concepts wait on the horizon. Antimatter engines annihilate matter and antimatter to produce pure energy, offering the ultimate specific impulse. A fraction of a gram of antimatter could propel a spacecraft to Mars in weeks. The The problem is producing and storing antimatter. Current production methods are incredibly inefficient, creating only a few nanograms per year at a cost of billions of dollars. A practical antimatter engine remains a long-term challenge, but the theoretical potential is so large that research continues. Solar sails take a completely different approach. Instead of carrying propellant, they rely on the pressure of sunlight itself. A giant, ultra-thin reflective sheet catches photons and slowly accelerates. No fuel is needed, but the thrust is extremely gentle. A solar sail could reach high speeds over many months of continuous acceleration, making it ideal for long-duration cargo missions or for sending probes to interstellar space. The Planetary Society's light sail missions have demonstrated the basic principle in Earth orbit. Scaling up to a sail the size of a football field would allow a spacecraft to reach the outer planets without any conventional fuel. All these advanced propulsion systems share one thing in common: they reduce travel time dramatically. That reduction is not just a convenience, it is the foundation for a regular, affordable transportation network between worlds. When a trip to Mars takes 6 to 9 months, only highly motivated specialists and government astronauts can make the journey. When that same trip takes 2 weeks, tourists, business travelers, and families can follow. The cost per passenger drops and the volume of traffic rises. The economy of a multi-planetary civilization depends on that kind of throughput. But even the fastest rocket cannot change one fundamental reality. The human body was designed for Earth's gravity, atmosphere, and radiation environment. No matter how quickly we travel, the destinations will still be hostile. That leads to an inevitable question. If we cannot change the planets, maybe we can change ourselves. The next milestone explores the idea of modifying the human body to thrive in space, a path that blurs the line between natural evolution and deliberate design. We arrive at a profound choice: adapt the body or adapt the worlds. For centuries, humans have changed their environment to fit their biology. We build homes, wear clothes, and heat our shelters. But on a world with 1/3 gravity and a thin, unbreathable atmosphere, no amount of clothing will make the air safe to breathe. No heater will stop the cosmic radiation that penetrates even thick walls. The alternative is to change the biology itself, not through evolution over millions of years, but through deliberate, careful intervention in a single lifetime. This is the milestone of human genetic and biological adaptation, and it may be the most controversial step on the entire journey. The first tools are already in use on Earth. CRISPR, a gene-editing technology discovered in the early 2010s, allows scientists to make precise changes to the DNA of living organisms. It has been used to correct genetic diseases in animals, to create crops that resist drought, and to alter the immune systems of pigs so their organs can be transplanted into humans. The same technique could one day be applied to astronauts headed for Mars. The goal would not be to create superhumans, but to give them a better chance of surviving the harsh conditions they will face. For example, a genetic tweak that boosts the body's natural antioxidant defenses could help cells repair damage from radiation. Another modification could increase bone density, counteracting the loss of mass that occurs in reduced gravity. A third could improve the efficiency of DNA repair mechanisms, reducing the long-term risk of cancer from cosmic rays. These changes are not simple. Each gene has multiple functions, and altering one can have unintended consequences. The ethical questions are equally complex. Do we have the right to permanently change a person's genome before they are born? What if the modifications are passed down to their children, creating a lineage of space-adapted humans who can never comfortably return to Earth? Some researchers argue that we should only use somatic gene therapy, which affects only the individual, not their offspring. But for a permanent colony that must thrive for generations, germline modifications may eventually be necessary. The children born on Mars will inherit the same vulnerabilities as their parents unless we change the blueprint. Cybernetic enhancements offer a different path. Instead of rewriting DNA, engineers can add hardware to the body, like a smart watch but integrated more deeply. Artificial retinas could improve vision in dim Martian light. Exoskeleton suits could reduce the strain of moving in partial gravity. Implantable sensors could monitor vital signs constantly and release medicines automatically. A small chip in the brain could interface directly with a computer, allowing the user to control machines with thought alone. None of these require altering the human genome. They are prosthetics but far more advanced than anything we have today. The challenge is making them reliable, safe, and power-efficient over years of use. Synthetic biology goes further. It combines engineering with biology to create entirely new organisms or systems. A team could design a bacterium that lives in the human gut and produces a protective enzyme that breaks down radiation byproducts. Another could engineer a yeast that synthesizes vitamin D from Martian soil minerals, preventing the deficiency that would come from reduced sunlight. These microscopic helpers become part of the extended human ecosystem, supporting the body without changing its own cells. The milestone here is not just about survival. It is about making the human body as resilient as the machines we send into space. The ethical debates around these technologies will shape how quickly they are adopted. Some people see any form of genetic modification as tampering with nature, a line that should not be crossed. Others point out that we already use medicine, vaccines, and glasses to overcome natural limitations, so the difference is one of degree, not kind. A middle ground might be to allow modifications only for medical necessity, such as preventing radiation-induced cancer or preserving bone density, while prohibiting cosmetic or enhancement changes until far more is understood. The colony itself will have to decide these rules because Earth-based regulators are too far away and too slow to react to local conditions. If we succeed in adapting ourselves, the result could be a branch of humanity that is physically different from those who remain on Earth. Martians might be taller and more slender due to low gravity, with denser bones and more radiation-resistant cells. They might have darker skin to protect against the higher ultraviolet levels on the surface. Over generations, natural selection would also play a role. Those with genes that confer better resistance would have more children, and the population would slowly shift. But with genetic tools, that process could be guided rather than left to chance. The question of what it means to be human becomes open-ended, a continuous experiment in adaptation. This milestone leads directly to the next frontier. Once the human body is equipped to handle the stresses of space, the entire solar system opens up. The asteroid belt is the next logical target. It holds the raw materials to build new habitats, new ships, and new industries without ever returning to a planetary surface. A permanent presence there among the rocks becomes a stepping stone to the outer planets and eventually to the stars. The same genetic and cybernetic tools that help us survive on Mars will make living in the belt, with its microgravity and isolation, not just possible but comfortable. We are beginning to design ourselves for a future that no longer depends on a single world. The rocks that drift between Mars and Jupiter are not dead. They are rich with the elements of life and industry. Water ice locked inside carbonaceous asteroids can be split into oxygen and hydrogen, the rocket fuel that powers our expansion. Metals like iron, nickel, and cobalt float freely in metallic bodies, ready to be shaped into beams, hulls, and pressure vessels without ever being hauled up from a gravity well. Organics, the carbon-based compounds that form the building blocks of life, are scattered throughout the belt. A single asteroid a few hundred meters across could hold more water than 1,000 tanker ships from Earth. This is not a barren wilderness. It is the most abundant resource zone in the inner solar system, and the next logical home for a civilization that has outgrown its cradle. Building a permanent colony here requires solving two fundamental problems. The first is low gravity. Most asteroids have a gravitational pull so weak that a person could kick off the surface and drift away into space. Walking is impossible. Even a gentle push sends you tumbling. Living in that environment for months or years would accelerate the bone and muscle loss that already plagues astronauts in orbit. The solution is to create your own gravity through rotation. A habitat tethered to a large asteroid could spin slowly, generating centrifugal force that mimics Earth's pull. A free-floating station like an O'Neill cylinder, a rotating ring kilometers in diameter, would provide a comfortable living environment with fields, lakes, and towns along its inner surface. The rotation rate would be just fast enough to produce one Earth gravity at the rim, while the center axis remains weightless for industrial processes. The materials to build that cylinder come from the belt itself. Iron and nickel are refined into structural rings. Water is split for atmosphere and fuel. Silicates become concrete and glass. The colony becomes a self-contained world, independent of any planet. The second challenge is distance. The asteroid belt is roughly 2 to 3 times farther from the Sun than Earth. Sunlight is weaker, so solar panels need to be larger, but nuclear power or advanced solar concentrators can bridge the gap. Travel time from Earth to the belt is measured in months with chemical propulsion, but a permanent colony will rely on a fleet of tugs and tankers that make the trip regularly. Once the infrastructure is in place, the belt becomes a hub for interplanetary commerce. Mining operations extract water and metals, refine them on site, and ship them to depots at Mars, Earth, and the outer planets. The colony grows from a small outpost into a network of habitats, each specializing in a different resource. Some are carved directly into the interiors of large asteroids, tunneling through rock to create pressurized chambers. Others float free, connected by pressurized tubes or traveling in formation. The society that emerges is decentralized, entrepreneurial, and deeply connected to the rhythm of a sun that rises and sets not on a horizon but on a calendar of orbital mechanics. This milestone marks the moment when humanity ceases to be a single planet species and becomes something far more distributed. We are no longer just colonizing a second world. We are settling the gaps between worlds. The asteroid belt is a stepping stone to the outer solar system. From here, the moons of Jupiter and Saturn are within reach. A spacecraft can refuel at a belt depot, then accelerate toward the gas giants with a full tank. The same infrastructure that supports mining also supports exploration. A small team of scientists can live in a habitat that drifts through the belt, studying asteroids up close, then hop to a new rock when the old one is exhausted. The belt becomes a highway, not a wall, and once that highway is built, the next leap becomes inevitable. We will look outward past Jupiter, past Saturn, beyond the heliosphere, and ask ourselves the same question that drove us from Africa to the Americas and from Earth to the Moon. What lies out there? The first interstellar probe will be built not on Earth, but in the factories of the belt, assembled from materials that were born in the debris of ancient stars. That probe will carry a message from a multi-world species, one that learned to live not just on a single planet, but among the stars themselves. The belt colony is the forge where that future is hammered into shape. From the belt, the nearest star is only 4 light-years away. That distance, vast beyond everyday understanding, is the next frontier for a species that has learned to live on multiple worlds. The body of the solar system has become a familiar neighborhood. The next step is to send something beyond the sun's influence, an interstellar probe that carries the ambition of a civilization no longer bound to a single star. This milestone is not about colonization, at least not yet. It is about proving that we can reach out and touch another star system, even if only with a fragile, robotic messenger. The practical value is immense. A flyby of Alpha Centauri would return data about its planets, its stellar environment, and the conditions for life around another sun. But the symbolic value is even greater. The moment that probe leaves the heliosphere on a trajectory toward another star, humanity declares that it is no longer a prisoner of its own solar system. Several concepts are already on the drawing board. Breakthrough Starshot is the most famous. The idea is to build a tiny spacecraft, no larger than a postage stamp, attached to a paper-thin sail. A powerful laser array on Earth would focus a beam of light onto that sail, accelerating the craft to a fifth of the speed of light within minutes. At that velocity, the probe would reach Alpha Centauri in just over 20 years. The science required is staggering. The sail must survive intense acceleration. The tiny craft must communicate across 4 light-years with a laser that is bright enough to be seen from Earth. And the target must be reached with enough precision to capture images of any planets in the system. This is not a project for the next decade, but the principles are sound and the engineering is being actively researched. Another promising avenue is fusion-driven propulsion. A spacecraft equipped with a compact fusion reactor could accelerate continuously for years, reaching velocities far beyond any chemical rocket. The same fusion technology that powers a colony on Mars or a ship in the belt could be adapted for interstellar travel. The exhaust from a fusion drive would be incredibly fast, and the fuel, isotopes of hydrogen, is abundant throughout the solar system. A fusion-driven probe could reach the Oort cloud, the distant shell of comets at the edge of the Sun's influence, in a few decades, then continue on to the nearest stars. Even more advanced concepts rely on propulsion that we have not yet invented. Antimatter engines, if they ever become practical, could achieve relativistic speeds by converting matter and antimatter into pure energy. A fraction of a gram of antimatter would be enough to push a probe to a significant fraction of light speed. Other ideas involve beamed energy from giant solar collectors in orbit, or even ramjet collectors that scoop up interstellar hydrogen as the craft moves. These technologies remain in the realm of theory, but they show that the path to the stars is not blocked by any fundamental law of physics. The first interstellar probe will likely be a combined effort of many nations and private organizations, drawing on the manufacturing capacity of orbital shipyards and the resource wealth of the belt. It will be the most ambitious machine ever built by humans, designed to operate for decades without any possibility of repair or resupply. Its launch will be a ceremony that bridges centuries of exploration. And its arrival at another star system, even if only an image of a distant world, will change how we see ourselves. That probe is the bridge between a multi-planetary civilization and an interstellar one. With its launch, we prove that the Sun is not a cage but a departure point. And once that proof exists, the final milestone stands waiting. A civilization that is not just spread across planets, but sustainable, thriving, and capable of existing for millennia without relying on a single home world. A civilization that no longer needs Earth is the point of no return. That is the final milestone, and it is not a single event. It is a gradual shift, a slow tipping point where the number of humans living off Earth becomes so large and their systems so self-reliant that the survival of our species no longer depends on any one planet. When that happens, humanity becomes truly multi-planetary, not as a temporary visitor but as a permanent resident of the solar system. What does that civilization look like? Mars is no longer a scientific outpost. It is a network of cities, some buried under regolith for radiation shielding, others built inside ancient lava tubes. They have their own industries, their own farms, their own power grids. The same is true of the Moon, where a thriving community works in manufacturing and tourism. Orbital habitats drift around Earth, the Lagrange points, and the asteroid belt, each one a world of its own with its own laws, its own currency, and its own customs. Millions of people live their entire lives without ever setting foot on Earth. Some of them never see a blue sky. They grow up under the glow of artificial suns and the steady hum of life support systems. But they are not prisoners. They are citizens of a civilization that spans dozens of worlds. The economy that supports them is robust because it is diversified. Water from the Moon fuels ships. Metals from the belt feed orbital shipyards. Rare pharmaceuticals grown in microgravity are traded for Earth goods. The currency is a digital token accepted from Mercury to the outer moons. Trade routes are as regular as bus lines, with nuclear-powered freighters moving between depots on a predictable schedule. Investment flows from Earth into new colonies, and returns flow back as resources and intellectual property. The entire system is self-financing, no longer reliant on government subsidies. Governance evolves alongside the economy. The old model of a single Earth government controlling everything becomes impossible. The distances are too great, the cultures too varied, the interests too distinct. Instead, a patchwork of planetary and orbital governments emerges, linked by treaties and mutual dependence. A Martian colony might elect its own council, while an asteroid habitat operates as a cooperative. A charter of human rights, adapted for life in space, sets the baseline for how people are treated regardless of where they live. Disputes are resolved by arbitration or by a court whose jurisdiction extends across the system. The legal framework is flexible enough to allow innovation but strong enough to prevent exploitation. This civilization does not stand still. It is built to expand. The same rockets, factories, and habitats that made Mars possible can be adapted for the moons of Jupiter. The same closed-loop life support systems that sustain a city in the belt can keep a generation ship alive for centuries. The direction of expansion is always outward, toward the cold and the dark, because that is where the next resources and the next challenges lie. There is no single destination. The frontier is wherever humans have not yet arrived. The point of no return is not declared by any single leader. It is felt when the first generation of children is born on Mars and grows up to have their own children. It is seen when a factory in orbit produces a Starship component without a single Earth-mined atom. It is heard when a teenager in a Jovian habitat argues with a cousin on Earth about something that happened on a station near Saturn. At that moment, the umbilical cord is cut. Earth is still the home world, the place of origin, but it is no longer the only home. The human species has become a multi-planetary civilization. What started as a dream of leaving the cradle has become a permanent reality. The 25 milestones we have traced are not a checklist that you finish and set aside. They are the foundation of a way of life that must be maintained and renewed with every generation. The first rocket landed safely. The first fuel depot was built. The first greenhouse grew food. The first child took their first steps on another world. Each of those moments was a victory of ingenuity and courage. But the work does not end. The biosphere must be tended, the laws must be updated, the ships must be built. The next milestone is always ahead, and that is the legacy of this journey. It is not about reaching a destination. It is about becoming a species that can keep moving, keep exploring, keep building, no matter what obstacles arise. The footprints on Mars will fade. The cities in the belt will age. But the civilization that made them will persist because it learned to live not just on one world but on many. That resilience is the true gift of every person who looked at the stars and refused to call them unreachable. Every milestone we have traced shares a single thread. Each one makes the next possible. Reusable rockets gave us cheap access. Orbital refueling made deep space missions feasible. Lunar bases taught us to live off the land. Mars colonies will teach us to build a new world. The journey from a single planet to a multi-species civilization is not a straight line. It is a ladder where every rung supports the one above. And the most important thing to understand is that we are already standing on the first rungs. The first truly reusable boosters are landing on drone ships right now. Astronauts are growing lettuce on the International Space Station. Engineers are designing nuclear thermal engines for test flights within a decade. The first milestones are not distant dreams, they are happening in our lifetime. That means the future we have described is not a fantasy, it is a trajectory. Every decision we make today, every investment in research, every student who chooses a career in engineering or biology or space law pushes the ladder a little higher. The 25 milestones are a map, but the map is useless without travelers. You are one of those travelers, so we want to hear from you. Which milestone excites you the most? Is it the moment a human first steps onto Mars? The day an asteroid miner brings back its first load of platinum? Or the quiet revolution of a closed-loop biosphere that finally breathes on its own? Let us know in the comments. Share your thoughts, your questions, your own visions of how we get there. The conversation is part of the journey, and if you want to continue exploring the road ahead, subscribe and stay tuned. The next video will dive deeper into one of these milestones, unpacking the science, the challenges, and the people who are making it real. Because the future is not something that happens to us, it is something we build one milestone at a time. Thank you for being part of that story.